we've been talking about trees for a long time now, and today we're also going to talk more about trees. So consider this problem. In the input, I have some tree, and this tree might even be weighted. So maybe I have weights on my edges, but this doesn't really change the problem much. So I say maybe in the input, I also have a weight function, which takes edges and gives them weights. And then I have a bunch of queries. These are also, of course, part of the input. And every query just gives me two different vertices and asks me what is the distance between these two vertices. Okay, so a query just gives me two vertices, and the answer to this query, which is what I should output, is basically the distance from U to V in this tree T. Okay. Of course, there is a trivial way to solve this. Every time that someone asks for a query, you can just do a DFS, right? And you can find the distances. Even if it's weighted, you can do a DFS because it's a tree, right? So there is exactly one path between U and V. As long as I find that path, I can just sum up the weights of all the edges on that path. So I don't need to do anything interesting here. I don't need to really do Dijkstra. I can just do DFS, or I can also do BFS. But that would mean that every query is going to take ON time to answer. And of course, I'm never happy with that. I want to always answer my queries much faster. Okay, so this is our trivial solution. Basically, I'm going to do no pre-processing at all. But even if I don't do any pre-processing, I have to read the graph. So it's just ON time for pre-processing. And then it's also ON time for every query. Now, of course, the question is, can I do better than this? Imagine that I have n queries. If I have n queries, my total runtime is n squared right now. I want to reduce my total runtime. I want to be able to do the queries faster. Okay. Now, this gets us into a problem which is called lowest common ancestor. Okay, so let's say I have my tree. I might have a very complicated tree, and it's not a binary tree. It can have, every vertex can have any number of descendants or children or so on. So let's say this is my tree. And suppose that I'm given two vertices. So maybe I'm given this vertex U and this vertex V. And the question is, what is the distance? Okay. Now, I'm doing it without weights on the edges, but all of the algorithms that I'm going to talk about work also with weighted edges. Now, you have to just look at the path from U to V. How does that path look like? I start at U, and I keep going up for a number of steps, right? So I'll go up, up, up. And then at some point, I have to go down until I reach V, right? So basically, the path from U to V starts from U, goes to the ancestors of U, and keeps going up until it reaches an ancestor of U that is also an ancestor of V. And then it goes down. Now, for this particular U and V that I wrote here, there is only one common ancestor, which is the root. So let me try another combination. Let's say my U is this one and my V is this one. So now from U, I go to this ancestor. Because it's also an ancestor of V, I go down. This is the path from U. So if you look at all of the ancestors of U, who are the ancestors of U? These are the ancestors of U, including U itself, actually. Right? And who are the ancestors of V? Well, these are the ancestors of V. Now, the interesting point is if you look at the common ancestors, the two vertices up here, you see that specifically, if you look at the lowest common ancestor, that's the ancestor that is definitely between U and V in the path in the tree, right? So if I want to find the distance from U to V, I can just who the lowest common ancestor of U and V is, right? And then suppose that I have also saved levels in my tree, so I know what the level of every vertex is. So then I would know the number of edges that I have to take. I have to go from U to the lowest common ancestor. Let's call the lowest common ancestor something. Let's call it L. So I have to go from U to L. The number of edges here would just be the difference in the levels of U and L. And then I have to go from L to V. Again, the number of edges would be the difference between the levels of L and V. So if I somehow had a magical way of finding lowest common ancestors, I could actually answer these distance queries really fast. I could just find one lowest common ancestor, and as soon as I find the lowest common ancestor, I have constant amount of work, right? And of course, I'm also calculating those levels, let's say in the pre-processing, because I'm doing ON pre-processing anyway, I can just calculate the levels of all of the vertices as well. Okay. Now, and again, this is the unweighted version. We will see the weighted version very soon. So the question is how to find this lowest common ancestor. But I'm going to simplify this a little bit. So let's look at a simpler problem first. And this is my simpler problem. I say that my input is exactly like before. I have a tree as my input. But now my queries, instead of asking me to find the distance between two nodes, they just give me some node and they tell me that I want to start at this node and go up by a number of steps. And I have to answer, where do I end up? Okay, so every query is going to give me a vertex U, and it's also going to give me a number K. And the answer to this query is basically who is the, or where is the kth parent of U. Or if you think of parent as a function that takes some vertex and gives me the parent of that vertex, basically I'm asking what happens if I apply the parent function K times. Okay, what is this? So for example, if K is 3 and U is here, I want to go up by 3 steps, I will end up at the root, right? If K is 2 and U is here, I'll go up by 2 steps, I'll end up here. Now, remember how we used to save our trees? We usually save our trees by just knowing the parents and the children of every node. Sometimes we only save the parents, sometimes we only save the children, sometimes we save both. So again, here, I have a very simple, trivial way of answering the question. I just start at U, and for K times, I keep going to the parent, right? And if I do that, I'm basically answering every query in OK, but K can be at most N, so that's bad. I'm spending ON time to answer a query. I'm not happy about this. I want to be able to answer my queries faster. Now, you might have also noticed that, well, K is at most the height of the tree. So instead of saying N, I can say I'm answering every query in OH. But here I don't have any control over my tree. So the tree is part of the input. I cannot balance this tree. It's just something that is given to me, right? So here's the simple idea that we're going to use, and it's actually a form of dynamic programming. I want to basically create a list of all the parents of the current node, okay? But if I put all the parents in, the list might get really large. Again, imagine in the worst case, I have, let's say, a tree that is just a very long path. And if at every node I save all of its ancestors, then I have to just save n squared values, or n squared values. And that's not something that I would like to do. So instead, I want to say at every node, I'm going to save only some of the parents. Now, which parents? Since we're computer scientists, we like powers of 2. So I'm going to save all the parents whose distance to the current node, all the ancestors whose distance to the current node is a power of 2. Okay, so this is what I'm going to do. My DP is going to have U and I, where U is a vertex and I is just an integer. Okay, a positive integer or non-negative integer. And I want this value to basically be the ancestor of U that is 2 to the power of I steps or levels above U. So for example, ancestor of U0, this would just be the parent of U, right? This is very easy to figure out. And so this is also the base case of my dynamic program. Okay. But now generally, let's say that I want to find UI, the answer for UI, which means that I want to start at vertex U, and I want to say what happens if I go up my tree for 2 to the power of I steps. Where would I end up? Okay, and by the way, so that everything makes sense, you can just imagine that I know the levels and I calculate these things only when 2 to the power of I doesn't get me any farther than the root. Okay. Or another way is to just say root is its own parent. So if you get to the root, no matter how much you go up, you're going to stay at the root. Okay. Anyway, so I want to find the ancestor of vertex U that is 2 to the power of I levels above. What can I do? Well, I can first go half of the way up. So I can say I find the ancestor that is 2 to the power of I minus 1 steps above. Right? And then from there, I say, take the other half. Go another 2 to the power of I minus 1 steps up. Okay? So something like this. Another 2 to the power of I minus 1. Okay. So I can calculate it like this then. I can say, let's find this middle point. Let's call it M. And this is just going to be the ancestor of U I minus 1. Right? And then this ancestor of UI is just going to be the ancestor of M I minus 1. Okay, so this was the vertex M. I started at vertex U. I went up by 2 to the power of I minus 1 steps. I got to M. If from M, I again go up by 2 to the power of I minus 1 steps, I will get to the same place as if I had gone up from U by 2 to the power of I steps. Now, this is easier to understand, but again, in code and also here, the way I would write this is by just combining everything. So it's like this, U I minus 1, I minus 1. Okay. Again, this is doing exactly this. Nice. So now I have a dynamic programming formulation. Again, I have to say, how do I order my subproblems? And it's kind of obvious, right, from top to bottom. Because when I want to find the ancestors of U, I'm only looking at the ancestors of M, and M is something that was above U anyway. Right? So top to bottom, and of course, in increasing order of I. Nice. So this is my pre-processing. In my pre-processing, I'm going to find all these ancestors that are at a distance that is a power of 2. Now, how much time am I going to spend here? Well, the height of my tree is at most n. So at each one of my nodes, I'm calculating at most log n different ancestors, right? And I have n nodes, so it's n log n. And for every ancestor, of course, I'm spending constant time. So my pre-processing time is now O n log n. Now, but I wanted this. I want to be able to also answer something like this. Who is the kth parent of U? Okay. How can I do that? How can I answer a question like this? Well, I can just draw it. So let's say I have this vertex U. So this is answering queries. And I want to start from U and I want to go up by k steps. And the question is, what is the vertex here? Okay. I know how to go up by a power of 2. So let's just find the largest power of 2 that I can find that is less than k. And let's go up by that many steps, right? So I'll just go up by something. Let's say some 2 to the power of I. But this was the largest possible I that I could choose, such that 2 to the power of I was less than k. Less than or equal to k. And now from here, from this new point, I know that I have to go up by k minus 2 to the power of I steps. So I just continue this recursively. I again take the largest power of 2 that I can take, and I just continue that until I get to the results. Okay. So how much time will this one take? Yeah. So this is actually going to take O log k time. Now, this is interesting because here's the thing. How is it O log k? Suppose I write the number k in binary. Okay. So let's say my number k is something 1 0 0 1 1 1 0 1 0 in binary, right? What is the largest power of 2 that is smaller than k? It's just 1 and then followed by all zeros, right? So with my first jump, I'm basically covering this much. I'm covering this. This is a power of 2. And then the remaining amount would be this. And then by next jump, I'm going to cover the next power of 2, which is basically the next 1 in the binary representation of k, and so on. So the number of jumps that I'm going to take is basically equal to the number of 1s in the binary representation of k. But that's at most log k. Okay, because the number of digits is log k. Great. Or another way of looking at this, another interesting way of looking at this is that I will never have 2 jumps of the same length. Because if I could have 2 jumps of length 2 to the power of I could just have 1 jump of length 2 to the power of I plus 1. Right? And that also shows that all of my jumps are different. Okay. Let's actually code this. I'm going to be a little bit lazy, and I'm going to say in the input, I'm getting the tree by just getting the parent of every vertex, right? So I don't want to do a DFS to decide like who's the parent, who's the root, and so on. So I'm just going to have an array called parent. And let's say my maximum n is something like this. And I read some number n. And then I say for every I from 1 to n, just read parent of vertex I. And I'm assuming that the vertex is the root if it's its own parent. Okay. So this is reading everything. And now I want to do this dynamic programming. I want to do my pre-processing. For every vertex U, I want to find all of the ancestors that are above it by some power of 2. So actually, here's the thing. I call this max log. Let's say my log is at most something like 20, and then I say my max n is just 2 to the power of max log. And let me just add some plus 10. Okay. So I want to know how many elements I want to save here. That's why I'm doing that. So I would have my dynamic programming, my ancestors. For every vertex, I have up to max log possible values here. Okay. Now let's just go ahead and fill this up. I need to know who the root is, right? Because I need to fill this up from the top down. And I need to also know who the children of every node are going to be. So I'm going to save my children. Vector. Let's say I have a vector called children for every one of my nodes. And when I read the parent of vertex I say that if parent of I is not I itself, then I is a child of its parent. Right? So children parent I dot pushback I. Otherwise, if parent of I is I itself, I just remember that my root is vertex number I. Okay, so I have my root as well. Nice. Now, I'm just going to fill up this ancestor. I'm going to call that pre-process, and I just pass it some vertex. I want to start at the top, so I say start with the root. And this is my pre-process, and it takes some vertex u. Okay. Now, at this vertex u, I want to first calculate all the ancestors of u. But after I did it, I want to then go and recursively call pre-process on all the children of u. And because I don't have a good memory, I want to first write this, because otherwise I will forget it. So I say for every v that is a child of u, remember to call pre-process on v at the end. Okay. Now, at u itself, I have to do these things. So I have to say the ancestor of u, 0, is just going to be parent of u. And then for every other value, for every I from 1 to max log, ancestor of ui is going to be this. Ancestor I minus 1, and then here we have ancestor ui minus 1. Okay. So this is all of my pre-processing. It just starts at the top of the tree, calculates all the ancestors at distances that are powers of 2 for the current node, and then it goes to all the children and does the same thing. Okay. Now that I have all of these things, I can answer my queries. So let's say I read the number of queries. Let's call that M, or whatever. I just keep reading queries. Let's say I have U and K. I say, as long as you're giving me queries, I will read them. And I should just, let's have a different function for this. So I just say, write the query UK. Okay. Now I have a function called query. It takes a vertex u and some number k, and it wants to start at u and go k steps up and tell me what is the ancestor that is k steps up. Okay. Now, at this point, I need to find the largest power of 2 that is smaller than k. Right? How am I going to find it? I can just do a for loop and figure out what is the largest power of 2 that is smaller than k, right? So some of you are looking funny at me. I'm going to do it, and then you'll see that it's wrong, and we'll figure out how to do it correctly. Well, it's not wrong, it's just not optimal. So let's say I start with some number I, and originally I is 0. And I say while 2 to the power of I is less than or equal to k, increase I. Okay. Now, this is not exactly correct because I have to say 2 to the power of I plus 1 before I increase I, but that's not the issue that I wanted to talk about. So let's do this. So now I found the largest power of 2 that is smaller than k. And now I'm just going to say, well, let's do this. Let's start from u and let's go up by 2 to the power of I steps. And let's call this one v. So I say v is the ancestor of u that is above it by 2 to the power of I steps, right? And then I say return the query from v. Now from v, I have to go up by k minus 2 to the power of I steps. So k minus 2 to the power of I. Okay. Now I should have a base case. I can use 0 or 1 or both of them as my base case. So I can say if k is 0, just return u. If k is 1, just return parent of u. And otherwise do all of this. Okay. What's wrong with this query? Why is this not the same as the algorithm that I just taught you here? So you see this algorithm and see this implementation. They're not doing the same thing. They're not doing the same thing because every time I have to run this while loop and I have to find the power of 2. I have to find the largest power of 2, right? So every time this while loop is actually taking log k time. And I'm running the while loop log k times, so it's log squared of k now, right? So this is what's happening. So if my k is this, my while loop is starting at the end and just going forward, seeing what is the largest power of 2 that it can find, which is smaller than k, right? But then after I subtract that, I'm going to do the same thing again. I'm going to start from the end and keep going. This is awful, right? Because every time I'm just wasting this time. Basically, I mean, it's awful by a factor of log k. So instead of having O log k, I have O log squared k. But I don't want that. I want O log k. So what do you suggest I would do? Well, instead of doing this, I can start from the left side. I can start from the largest possible power of 2. And I can keep dividing by 2 until I'm smaller than k, right? That gives me the largest power of 2 that is smaller than k. And then I do my jump, but I also remember what the length of my jump was, so that the next time I don't start from the beginning. I just continue from where I started last time, from where I jumped last time. Okay. So this is what's going to happen here. I'm going to have some value called max I. So this is the maximum I that I might want to try. And originally, like the default value is just max log, right? And then here, instead of doing this, I say, let's start from this max I. And so I want to see, is 2 to the power of max I less than or equal to k or not? Okay. If it's not, I want to decrease my max I. So I say, while 2 to the power of max I is greater than k, decrease max I. Okay. And then here, I'm just going to use max I itself. But very importantly, when I do this jump by max I pass max I minus 1 to my function so that next time I know that I have to start from max I minus 1 when I'm trying to find how much I can. So this makes sure that I go over every digit at most once. And this is how I get a runtime of O log k instead of log squared k. Okay. So this is just doing querying like this, which was basically telling us who is the case parent of u. We've solved this simpler problem. But remember, our original problem was not this. Our original problem was that I have u and v, and I want the distance from u to v, right? But in order to find that, we said that we should find the lowest common ancestor of u and v. So let's do this now. Let's say my input is the same as before. My query always gives me u and v. And the answer that I have to give to this query is the lowest common ancestor of u and v. I have to say who's the lowest common ancestor. Okay. How can I use this previous version to solve that? So for every vertex u, I can ask who's the case parent or case ancestor of u. But my question is, who's the lowest common ancestor of two different nodes? Who's the lowest common ancestor of u and v? Well, first of all, if u and v are not at the same level, well, I'm again imagining that I have calculated levels. So let's say u is here, v is here. If they're not at the same level, the first thing I should do is make sure the levels are the same. So start from the one that is further below and just go up by the number of steps required to have the same level. So I'm starting from u and I go here, let's say to u prime. And basically, how many steps is this? It's the level of u minus the level of v, right? So this is level of u minus level of v. Actually, I'm using level now, but I just remembered that in previous lectures I called it depth, I guess. Whatever, you know what I mean, right? Okay, so now we have them at the same level, and I want the lowest common ancestor of u prime and v. But again, the question is, where is this lowest common ancestor? Now, for any number k, I can ask, where is the case ancestor of u prime? Or where is the case ancestor of v? So I can just do a binary search on k, right? So I ask, who is the nth ancestor of u prime and who is the nth ancestor of v? The nth ancestor is definitely going to be the same because it's going to just be the root, right? And then I just do a binary search. I ask, is the first ancestor the same? Or is the 0th ancestor the same? Are they literally the same vertex? If not, then just do a binary search. Try n over 2. Then again, try n over 4 and so on. Just binary search on the value of k. Okay, so this is now my solution. I want to say find the smallest k such that the case ancestor of u prime is equal to the case ancestor of v. Okay, so parent k of u prime is equal to parent k of v. And since I want the smallest k with this property, I can just do a binary search. Now, how much time would this take? The binary search on k is going to go on for log n iterations. But every time when I'm asking who's the parent at this particular height, I'm also spending O log k, which is log n as well. So it's now log squared n. Okay, so this is going to take O log squared n to answer. Now, if I had not made that previous improvement here, then this one would take log squared n, and then this one would be log cube n. But again, I'm not happy about the extra log. I want to just do it in log n. I don't want to spend log squared n. Okay, so how do you suggest I do this in just O log n instead of log squared n? Okay, let me create this again. So remember, I have the vertex u, I have the vertex v. There is some path between them. And the first thing I did was to make sure they're at the same level, right? Now, instead of doing binary search, I can just say, let's find the largest power of 2 such that I can start from u prime and go up by that power of 2. And I can also start from v and go up by that power of 2. And I will not end up in the same place. Okay. So I'm saying my jumps are going to always be by powers of 2. But what is the largest jump that I can make? How much can I go up from both u prime and v such that I do not reach the same place? Okay. That's something that I can find. Right? So I can just look at all of the ancestors that I pre-computed for u prime and all of the ancestors that I pre-computed for v. And I can find this largest possible jump that gives me different ancestors. But of course, I'm only looking at jumps that have their lengths a power of 2, right? So let's say I jump up here by 2 to the power of I steps. And I also jump up here by 2 to the power of I steps. Now, because I didn't reach the same vertex, it means that I can continue my search from here. So I can find the lowest common ancestor of this vertex and this vertex. Right? And when I want to do that, again, I do the same thing. I ask, what is the longest jump, power of 2 jump that I can make such that I don't have the same vertex? So maybe I can do like some other power of 2 to the power of j, and so on. And I continue these jumps until I see that I cannot do any more jumps. So I find these 2 vertices, and these 2 vertices are going to have the same parent, right? And that parent is the lowest common ancestor. Now, this is pretty much like the previous algorithm, like this one. And I can make the same argument to say that I will never jump by 2 to the power of I twice. Because if I could do that, I would just jump by 2 to the power of I plus 1. Right? So this is actually going to take O log n time. Okay, let's code this one. This was called query. So I'm going to change the name from query to just ancestor. Okay. I have to also calculate the levels of the nodes. So let's say I do that in my pre-processing as well. So I have a level for every node. And whenever I'm doing pre-processing at U, I say that the level of U becomes 1 plus the level of parent of U. Now, with this definition, the level of the root becomes 1, right? And then the next level is 2, 3, and so on. But I don't really care if the level of the root is 0 or 1. It's fine. I just care about the differences between the levels. So this is going to work out. I have all of my levels now. And I did this now. My queries are going to contain 2 vertices now. And I say, while I read U and V, just write the lowest common ancestor of U and V. Okay. Now I have to write my lowest common ancestor. Now, the first thing we did was that we said U and V should be at the same level. So if they're not at the same level, the one that has a bigger level, which is like below the other one, we have to first do a jump from that. Okay. So I say if the level of U is less than the level of V, first of all, swap U and V so that I know that U is the one that has the bigger level, right? And now I change U. I say U becomes the ancestor of U. That is how many levels up? Well, level of U minus level of V. Okay. And now I know that my U and V are at the same level. Basically, this U is the U prime in the document. So now I can find the lowest common ancestor of U and V. How do I find this? Well, I'm just going to do what I did here. I'm going to say for every I that starts from max log -1, or okay, actually, let me do something like this, max log, so that I don't have any problems there. Where was I? Yeah. So for every I, if the ancestor of U at level like 2 to the power of I levels above is not the same as the ancestor of V 2 to the power of I levels above, I just say on both sides, I'm going up by 2 to the power of I steps. So U becomes ancestor of U 2 to the power of I steps above, and V becomes ancestor of V 2 to the power of I steps. Okay. And that's it. So at this point, I will find the lowest point, the lowest common ancestor, but not exactly that, like one level below it, right? So at this point, I just say return the parent of U. Okay. Now I have to have some base case here as well. If U is equal to V, just return U. Okay. And actually, well, I could have done it here. I could have done it after this part. When I change it, I say if U is equal to V, just return U. Okay. Otherwise, try to find how much I can go up without making the ancestor the same. And then, of course, if I just go up by one more step, which is just parent of the last node, that's giving me the lowest common ancestor. Okay. So now we have all of these things. What is our pre-processing time? Our pre-processing time is just ON. Because, ON log n. Because I'm doing these ancestor computations, which I already told you take ON log n. But I'm also calculating the levels for every node, and that's the part that's taking ON. Okay. And then every query, every lowest common ancestor query is answered in O log n time as well. Great. So now let's finally go to our original problem. So this was my original problem. I have a tree T. Forget about the weights for now. I get queries that give me two vertices and ask me what is the distance from U to V. Okay. How can I answer these queries? Well, we just said that from U, we have to go to the lowest common ancestor, and then from the lowest common ancestor to V. So the number of steps from U to the lowest common ancestor is just the difference in their levels. And then the same thing from the lowest common ancestor to V. So that's how we get the distance. We just sum up these two differences. Now, what happens if I have weights on my edges? What should I change in all of my algorithms if I have weights? Well, here, when I'm finding who's the ancestor of U 2 to the power of I levels above, I have to also say what is the distance to that ancestor. So what is the sum of the weights of all the edges between U and that ancestor, right? And I can easily do that. And again, it's just another DP in addition to this. So where do I put it? Well, let's say I write it very small here. D of UI is the distance from vertex U to ans of UI. So the ancestor that is 2 to the power of I steps. Okay. What is D of U0? That's just the distance from U to the parent of U. So that's just the weight of the edge between U and its parent, right? So whatever weight I had there, U and parent of U, that's going to be put here. Now here, when I wanted to find the ancestor of U that is 2 to the power of I steps above, I first found the ancestor that was 2 to the power of I minus 1 steps above. But I can also find the distance to it, right? And then I'm finding from here the ancestor that is again 2 to the power of I minus 1 levels above, and I can find the distance to that, and I can just sum the two distances. So if I want d of ui, I have first d of ui minus 1. This is the distance from u to this m, right? Plus d of this m and I minus 1. But remember, m was ancestor of ui minus 1. Okay. So that's how I find all of these distances. And then when someone asks me who's the parent that is k levels above, I can also find the distance to that parent. Again, just sum up all the distances as you're going up the tree, right? And this applies at all of these things, so I can find all of the distances. My runtimes don't change at all. I mean, they change by a factor of 2, but we're using the O notation. So my pre-processing is still O and log n, and every query is still O log n. I want to also consider another problem today. And this was a problem that we were solving using prefix sums. And then I told you that it would only work if our addition operator has an inverse. So remember, this was this problem. So I said that in the input, I give you some array. So let's say an array A of n elements. Let's say these elements are integers. And I said that I ask you a bunch of queries, and every query just gives you a segment and asks what is the sum of all the numbers in this segment. Okay. So every query is going to give you I and j, and the answer to this query should be the sum for k from I to j of ak. Okay. Now, we've already solved this using dynamic programming and prefix sum. It was a very simple idea. It was that I just saved the sum of all the numbers from 1 to I, right? So this was what I did. It was a prefix sum. I say sum I is basically going to be the sum of all the numbers from index 1 to index I, okay? And the way I actually calculated this was not like that. It was just that I said sum of 0 is 0. And then for every other I, sum of I is just sum of I minus 1 plus AI. Okay. And then when we wanted to do a query, basically we had this array. And let's say I want to find the sum of all numbers from index I to index j. We said that we first sum up all the numbers from the beginning to index j. So that's sum j. And then we subtract all the extra elements. So minus sum I minus 1. Okay. So we could do our pre-processing in linear time in ON, and then we could answer each query in constant time. Now, I told you that instead of sum, we can have other operations. So imagine if I had XOR, if I wanted the XOR of all the items between I and j. I could also do the same thing. Actually, XOR is its own inverse, so I would just take whatever sum of j XOR sum of I minus 1. Right. Now, I could do the same thing with product. But the thing is, all of these operations that I'm doing are actually reversible operations. They have an inverse. So when I have addition, I have subtraction. Multiplication has division, and so on. But what happens if my operation doesn't have an inverse? So let's say that I'm doing queries like this. So let's say I have the exact same input structure and query structure. Let me go to a new page. But then the answer that I expect for every query is now different. So the answer is going to be, let's say, the minimum item between indices I and j. So I say you have to output the minimum of k, or actually I can just write it like this instead, minimum of ai plus 1 to aj. Okay. So I'm doing these segment queries, but now I'm asking you what is the minimum item. Now, something like prefix sum would not work here, right? Because imagine if I have my array again from index 1 to n, and let's say this is index I, this is index j. And let's say I have defined something like this. I have said that mj is the minimum of all the items until index j, right? And let's say that mi minus 1 is the minimum of all the items until index I. So I know the minimum of these items, and I also know the minimum of these items. This is not going to help me at all about finding the minimum of the items from index I to index j, right? And basically the problem is that minimum is not an invertible operation. I cannot have an inverse for minimum, right? So now I cannot solve this using prefix sums. I have to figure out a better way. Now, how can I do any better than this? Well, here's one idea. Let's say that I have this array, and it's a huge array from index 1 to n. Actually, now that I think about it, for this particular algorithm, I prefer it if my indices are from 0 to n minus 1. Okay, so let's say my indices are from 0 to n minus 1. And I'm going to just divide this array into smaller chunks. And let's say that I divide it into chunks of size m. So I'm going to do something like this. I'm going to say, take everything from 0 to m minus 1. Then take everything from m to 2m minus 1. Then take everything from 2m to 3m minus 1, and so on. So just divide this array into chunks of size n. Okay. Now, maybe n is not a multiple of m, so my last chunk might be actually smaller, right? So all of my chunks are the same size, but my last chunk might be small. If that's the case, I'll just add some dummy items to the end so that my size becomes a multiple of my chunk size. And in this case, because I'm doing minimum, I would just add infinity to the end. Okay. So the idea is very simple. The idea is break the big array, this A, which was big, into chunks of size m. Okay. And let's now have another array. I'm going to call it B. And BI is just going to be the minimum item in the ith chunk. Chunk number I will go from I times m to I plus 1 times m minus 1. Right. Anyway, BI is the minimum item in the ith chunk. That's all you need to know. Okay. Now, if I do this, how much time do I need to calculate my array B? If I want to do this in my pre-processing, let's say. Well, I have to just go over my array A once and just find these minimums, right? So that's On. So my pre-processing right now is On. But now let's say I have to answer a query. So I'm given a query. It has given me I and j. And again, this is my whole array. And I have divided my array into a bunch of chunks. And now I'm given I and I'm given also j. So I want the minimum of all the items from index I to index j. How can I find this? Well, here's what I can do. I start from I, and I just keep taking the minimum. I find all of these items here, and I take their minimum until I get to the beginning of a chunk. When I get to the beginning of a chunk, I know the minimum of the entire chunk. So I can just jump to the end of it. And in one step, I know what the minimum was there. So I can just take the minimum of the chunk. So actually, another way of visualizing this is that I'm first jumping by one step until I get to the beginning of the chunk. And then I can jump to the end of the chunk. And then again, I can do the same thing. I can again jump by another chunk. And I keep doing this as long as my chunk ends before j. At some point, I get to this end of some chunk, and I see that the next chunk actually ends after j. So again, I have to take steps of size 1 now. So I have to start here, take the minimum, so on, until I get to index j. Now, my runtime is obviously the number of steps that I'm taking. So the question is, how many steps am I taking? And remember that my original array had n integers in it, and I said that my chunk size is m. Okay? So if I'm going from I to j, what is the number of these small steps that I can take before reaching a chunk? It's at most n. It's actually m minus 1, but we are doing O notation, so n. Right? And then how many big steps can I take? How many steps can I take that jump over an entire chunk? Well, every chunk has a length of m, and my total length is n. So I can take at most n over m such jumps. And then finally here I can have at most m jumps like this, the small jumps. So my total runtime for query is actually O m plus n over m. Okay. Again, the m was for the small jumps, and the n over m was for the long jumps. Okay. Now, until this point, I haven't told you what the value of m is. I just told you, imagine that I have some m, and I want to create chunks of size m. But now that I know my runtime, I want to choose m so that I minimize this runtime, right? So what is the best chunk size I can choose? Yes. So I'm going to say I take m to be square root n. Now, in practice, it has to be an integer, so maybe you can take floor or ceiling or whatever, but it doesn't really matter. It's like square root n. And so my runtime would be O square root n. And you can see that that's the best choice I could make for m, at least up to O notation, because no matter what value I choose for m, either m is more than square root of n, or n over m is more than square root of n. So you cannot get better than square root of n with this idea. And if you set m to be square root of n, then your whole runtime is O square root of n. Okay. Now, this is not as good as prefix sum, of course, where we could just answer the queries in constant time, but it's much better than having to go over the whole array every time. So I'm now answering every query in square root n instead of n. But what's interesting here is that I can actually have different things. Instead of just having queries, I can have other operations as well. I can also change my numbers. Okay. So here's another thing that I do. Maybe I have an operation that updates the number. So I give ix, and basically this means that change ai to x. Okay. Let's say I do that. So I take one of my numbers and I just change it. Now, what happens if I do an update like this? And imagine that I can have any combination of these operations. I can have a bunch of queries, a bunch of updates, then again, a bunch of queries, and so on, right? So I know how to do my queries, but whenever I'm doing an update, of course, I have to go and change the value in my original array A at index I to X, but I have to also update the value at the array B, right? But only the chunk that contains the index I is going to change potentially, right? So whenever I'm doing an update like this, I just recalculate the value for that chunk. So now I can do every update also in square root n times. So I have updates in square root n. I have queries also in all square root n. Now, and I don't need my operation to be reversible. But of course, if instead of min, I just had sum, the same technique would still work. I mean, it's not a good algorithm in comparison with prefix sum, but it would work. You can just have the sum of all the numbers, and you can also do updates to numbers. So what happens if I have sum instead of min? My query is still going to take O square root n time, but my update is now much faster, right? Because when I'm doing an update, when I'm changing AI to X, I know that I have to change position I of array A. I have to also change position I over M of array B, which is like the chunk corresponding to this. But in my array B, I'm now saving the sums, so I know exactly how much I have to change it. I don't have to go over the entire chunk. So if this was sum, I could actually update my elements in square root n time, and I could still answer queries in O square root n. Okay, sorry, I could update my entries in constant time, and I could answer my queries in O square root n, which is better than prefix sum, right? Because if I just had prefix sums, whenever I do an update, I have to go over my whole array of prefix sums and change all of those. So updating would take O(n) before. Now, so this kind of technique is actually useful in two cases now for us. It's useful when our operation is not reversible, and it's also useful when we have updates. Okay. Can we do better than this? Yes. And so this is the next data structure that I want to teach you about. It's a segment tree. Okay. So I want to go back to sum, but you can use XOR or multiplication or minimum or other operations. So my input is going to be just like before. It's going to be an array A of n integers. And then I'm going to have a bunch of operations. But I have two types of operations. Some operations update a value, and some other operations just ask for the sum of a segment. Okay, so two operations. I can have, let's say, actually, I'm going to write it like this: add ix, which basically means take AI and increase it by x. X can also be negative. Okay, so add x units to the ice number. And I can also ask for the sum ij, which should just return the sum of all the numbers from index I to index j. Okay. And let's say I'm also doing n operations. And these operations can be in any order. I have no control over my input. And my output is just going to be these answers, right? So this is my output. Every time that I'm asked for a sum, I have to output it. Now, I already know how to do my addition in constant time and answer my sum in square root n. But if I have n operations and I don't know what combination I have, this is going to give me a total runtime of n square root n. So I want to beat O(n) square root n. I want to somehow get something less than that. Actually, I'm going to get n log n. Now, this is the idea. I'm going to create a tree, and it's a binary tree. But I'm going to say that every node of my tree corresponds to some segment of my original array. Okay? So I say that the root of my tree corresponds to the entire array. Let's consider an array of size 4, let's say, because I want my size to be a power of 2. If it's not a power of 2, just add some elements, make it a power of 2, right? I'm lazy about these things. So let's say I have an array of size 4, or actually size 4, so it's easier to just do it like this. Okay, so my indices are 0, 1, 2, and 3. This is my array A. I'm going to create a tree, and I'm going to say that the root of my tree corresponds to the entire array. So it corresponds to the segment from 0 to 3, everything. But then every node is going to have 2 children. And the left child corresponds to the left half of the segment, and the right child corresponds to the right half of the segment. So I'm going to have the left child here, which corresponds to 0, 1, and the right child, which corresponds to 2, 3. And then this one is going to have a left child, which just corresponds to 0, and a right child, which just corresponds to 1. And here I'm going to have 2, and here I'm going to have 3. Okay. So this is what I call a segment tree, because it's a tree of segments, basically. It's a binary tree, but every node of the tree has an associated segment of the original array. Now, of course, I want to save something in these nodes. Actually, I want to just save the sum of the numbers in their corresponding segments, right? So let's say I have some numbers here. I don't know, let's say 5, 2, 1, minus 1, okay? So here at the leaves, I'm just going to save the numbers in my array. So at index 0, I have 5. At index 1, I have 2. At index 2, I have 1. And at index 3, I have minus 1. Now, at this node, I want the sum for the segment 0, 1. But that's just the sum of the blue numbers that I have at the 2 children. So I can just take 5 and 2, and I can say I assign 7 to this one. And here I want the sum of the items from index 2 to index 3. So I just take the sum of 2 children, that's 0. And again, here I just take the sum of the 2 children, it's 7. Okay. And that's, of course, the sum of all the items from index 0 to index 3 in my original array. So this is what I call a segment tree. So let's say I want to just maintain this tree. After every operation, I want to maintain this tree. And I also want to use this tree to answer my sum queries. So the first natural question is, how much time does it take to actually create this tree? N log n? Well, it's actually a little bit less. It's O(n), right? So what is the size of this tree? This tree has n leaves, right? So at the last level, I have n vertices. And then at the level above it, I have n over 2 vertices. And then at the level above that, I have n over 4 vertices, and so on. Okay? So if I sum all of these up, it's at most 2n. It's 2n minus 1, right? So I have O(n) vertices in this tree. So creating the tree itself is going to take O(n) time. And actually calculating these values for the first time, that's also going to take O(n) time, because I know the values at the leaves. And then it's just a bottom-up dynamic program, right? I'm just moving from the bottom of my tree towards the root. And at every node, I'm just taking the sum of the values of the 2 children. Okay? So my pre-processing, which is basically the creation of the tree, is O(n). Okay. Now, let's talk about this one. Let's talk about the updates. Let's say I do add ix, which means that I want to take the ith element and I want to add x units to it. So for example, let's say I want to do add 2, 2. So I want to take 2 and its current value is 1. I want to increase it by 2. It will become 3. Okay. Which values in my tree have to change? All the values that correspond to some segment that contains the index 2. Or in general, all the values of the segments that contain the index I. Right? So I can start at the top of my tree, and my root corresponds to a segment that has everything in it. Right? So the value at the root has to definitely increase. It has to increase by x. So instead of 7, I will now have 9 here. But then this index 2 is either on the left side or the right side. In this case, it's on the right side. So I can just move to the right side. And then I can update the value here. This also becomes 2. And then again, I see that index 2 is on the left side. So I go on the left, I update this value to 3. So in general, when I'm updating the value for a particular index, I have to go into my tree and I have to find all the segments that contain that index and I have to update their value, but there are log n such segments. And the way I find them is also super trivial. I start at the root contains the index I, and then every time I just ask, should I go left or should I go right to have index I in my segment? Okay. So this was also easy. I'm doing my add also in O log n time. What about sum? What if I want the sum of all the numbers from index I to index j? Well, again, I can start at my root and I can say, hey, I want the sum of all numbers from index I to index j. Let's say my I is 1 and j is 2. So let's say I'm doing sum of 1, 2. I can start at my root and the first thing I ask is this exactly the segment that I'm looking for? Is the segment from 1 to 2 the same as the segment of my root, which is 0 to 3? Unfortunately, the answer is no. So I can't just take the answer at the root. I have to go to its children. But now I say, well, I want the answer from 1 to 2. And since I want the answer from 1 to 2, I have to ask part of it from the left child and another part of it from the right child. So I want the answer, the sum from 1 to 2. I say, okay, I ask the left child for the sum from 1 to 1 because the left child only has information until index 1. And I ask the right child for the sum from 2 to 2. Okay. Now, again, at the left child, I see that, well, I have the sum from 0 to 1, but I'm looking for the sum from 1 to 1. Right? So I have to, again, go to the right child. I have to go here. But when I go here, I have the sum. It's just 2. Now, the same thing happens here. I want the sum from 2 to 2, but I have the sum from 2 to 3. So I just ask the left child, and that one has the sum from 2 to 2. So it just gives me this. And basically, I sum up these two, it's 5. Okay, so I know that I have to return 5. Okay, let's just write some pseudocode. So let's say that I have this sum. So I have sum ij. But let's say that other than I and j, I also have some node of my tree. Okay, and I'm going to call that node n. So n is a node of the segment tree. Okay, and basically what I want here is that I'm saying, what is the sum of all the items that are within the segment from index I to index j, but are also within the segment represented by this node. And this node is, of course, corresponding to some segment. Let's say n corresponds to something like n dot begin and n dot end, right? This is, let's say, the segments that I have at my node n. Okay, now what do I do? Very simple. I say if I is n dot begin and j is n dot end, or actually it's better if I just write it like this. If the segment ij that I'm looking for is exactly equal to the segment that I have here, n dot begin, n dot end, then just return whatever value you have in the current node of the tree. Okay? Return n dot value. But what if it's not the same? If it's not the same, then I have to basically ask both of my subtrees. I have to ask the left child and the right child. So I say if this is not the case, then return sum of ij n dot left plus sum of ij n dot right. Now, I didn't want to update my I and j. I want to actually update them before this if and else. So I want to move this down. And here, I want to say, well, what happens if this segment ij goes further than the segment that I have at my current node? I would just ignore everything that is outside of the current node anyway, right? So that means that j should become the minimum of j and n dot end, right? And the same thing from the other side. So I should become the maximum of I and n dot begin. Now, what happens if ij, the segment from I to j, did not have any intersection with the segment of node n at all? Then after I do this, I actually becomes bigger than j. So here I also say, if I is bigger than j, then return 0, because it's the empty segment. Okay? Otherwise, just do this. So it's a recursive algorithm. It's pretty easy to prove that this is correct, right? So it just finds the sum of all the elements that are within indices from I to j, and also within the segment represented by n. And of course, if n is the root of my tree, then everything is represented by it. So I can just get the sum of all the items from I to j. What's my runtime? This part is a little bit tricky. And I mean, we're running out of time, so we're going to see it next time. But if you look at it just naively, like the way the code is written, it seems that I want to find the sum at some node n. And in order to find it, I'm calling the same function, the same sum recursively on both the left child and the right child. So it seems that I might have to go over my entire tree to find this sum. And actually, in the example that I gave you, something like that happened, in the sense that I went all the way down to these leaves, right? So it seems that my runtime is O(n), okay, which would be terrible. If my runtime for answering the sum is O(n), I could just have a for loop and just sum everything, right? But we will see in the next session that actually we can do a better analysis. It's the exact same algorithm. I'm not going to change my algorithm. I'm going to just do a better analysis in the next session, and I'm going to show that this is actually taking O log n time. Okay. Great. So I'll see you at the exam in a few hours.